For people not necessarily versed in science, not necessarily all in science, and since you're not science majors, that's why I'm kind of going there. And honestly, even for people that really do like science, this section probably is the least favorite. And the only reason I say that is because they see this C word called chemistry, and it kind of scares people. So don't be scared. Don't be scared. We're going to get through this. It's going to be okay. We're going to start like I always like to do with every topic. We are going to start simple, understand the simple, and add a little bit more to it to make it more complicated and more complicated. We're going to go like that. Have you been in those classes where it starts out complex to start with and you don't have a clue and you just give up and you don't hear anything else? So we're going to start out simple first. And the way we're going to start out simple with our discussion of chemistry and biological molecules is we're first going to start at the atom. Do you remember our pyramid? What was at the very top, the smallest point of our pyramid? Atom. So it makes sense that we're going to start here. And so when we look at an atom, this is going to be the smallest unit of an element. If you start getting any smaller than this, we no longer have our elements of oxygen and nitrogen and hydrogen. They become something else. But what makes up all of our subatomic particles, if you will, are going to be these things that are called protons and neutrons and electrons. We have these three. We can handle three things, right? See, we're starting simple. And when we look at an atom, we're first going to see that the protons and the neutrons, they stick around the middle of the atom. The middle is called the nucleus, which is kind of good because the middle of a cell that has our DNA, what do we call that? That's also called a nucleus. So it's kind of in the same location. So our protons and neutrons are in the nucleus. Now, with these the big fancy names, subatomic particles, what does subatomic mean? What does sub mean? Below, like a submarine, marine meaning ocean, under the ocean. Subatomic meaning under an atom, smaller than an atom. That's all that means. And so when we look at these subatomic particles, while we pay attention to their location, it's going to be more important that we pay attention to the electrical charge of these elements. And again, we're working with three. It's going to be pretty easy, but it gets tricky. And I'm going to teach you how not to be tricked. I'm going to ask you trick questions in class. I'm not going to ask you trick questions on a test, okay? I promise. But I'm going to help you avoid those traps down the road. So the way that I remember the charge of a proton starts with a P. So what is its charge? Positive. See, P and P go together. That's the easy one. Now, the other subatomic particle that lives at the nucleus is called the neutron. This is where you can get tripped up. Because what's the first letter of neutron? Naturally, you might think N, well, if a P is positive, the N has to be what? Negative. That's a trap. No. The neutron is not negative. Why do you think a neutron, how do you think it maybe got its name? What does neutral mean? Doesn't have a charge. That's why we have that zero there. So neutron is tricky. Its whole name points to the fact that it's neutral, has no charge. And then our third subatomic particle are the electrons. And this is the only one that's not going to be at the nucleus. It's actually zipping around peripheral to the nucleus, much like our moon orbits the Earth, or the Earth orbits the sun. And it's the electron then that is going to be our negative subatomic particle. Now, when we look at our electrons and our protons, write this somewhere in your notes on your slides. In naturally occurring elements, protons equal neutrons. I'm sorry, electrons. Protons equal electrons. Why do you think it would be important for an atom to have the same number of protons and the same number of electrons? Neutral charge. They balance each other out. Nature, science, the universe is all about balance. So as we build our elements, hydrogen is going to be the simplest of our elements. How many protons does hydrogen have? 1. Its atomic number, and we'll talk more about that in a bit, is 1. So if I tell you the atomic number of hydrogen is 1, which means it has 1 proton, how many electrons is hydrogen going to have? 1, because they will equal out. Here's helium. Helium has an atomic number of 2. Don't look at the picture. I tell you helium has an atomic number of 2. How many electrons does helium have? 2. See how easy that is? I told you we were going to make this easy. Now the reason I stopped with helium before we look at any bigger atoms is that those first 2 electrons, the 1 in hydrogen and the 2 in helium, the way we package them together around the atomic nucleus is we put them in the same orbital shell. Now, these lines, these concentric lines that you see, like rings of a tree or the layers of an onion, these are conceptual to give us an idea of the energy level of these electrons. But notice, where do the first 2 electrons go? That number 1, that closest shell or closest orbital to our atomic nucleus. You can pack no more than 2 in that first shell. Did you hear me? The first shell only can hold 2. But before you pack any other electrons in other shells, and you see how we have a second one, a third one, a fourth one, and on, you have to fill up from inside out first. So here we have calcium. Calcium has an atomic number of 20. How many electrons does calcium have? Oh, y'all mumbled that. Come on. Calcium has an atomic number of 20. So how many electrons does it have? 20. See, it doesn't matter what the number is, how big it is. Doesn't have to be scary. It's the same. But with an atomic number of 20 and 20 electrons, where are you going to find the first 2 electrons? In the first shell. See, it doesn't matter how many. The first 2 always have to go into that first shell. Now, the other thing I want to point out, atoms are happiest, meaning they are the most stable, when their outermost shell is completely full. And you can see here with calcium, we've got 20 electrons, so we're going to pack our first 2 in that first shell. How many do we have left to pack? 20 minus 2, 18. It's like packing clothes in a suitcase. You got the little overnight bag, you put the first 2 items in that, now you got 18 more items, and how many more suitcases do I need? Guys need 1, ladies you need 50. I'll never get that, but you do. So, as we look at our other shells, our other suitcases to put our electrons in, understand they're all the same size suitcase. You're only going to get ever 8 electrons max in each suitcase. So we pack the first 2 of our 20 inside, we have 18 left. Where do we pack the next 8? Second suitcase, the second shell. So we pack 2, we pack 8, that's 10. How many do we have left out of 20? 10 more, okay. We get another suitcase out, it'll hold 8. We have 10, so we pack those 8. How many do we have left now? 2. Notice our outer shell, our last suitcase, 1, 2, 3, 4th suitcase, only has 2 in it. That's not very stable. Because you're dragging all those suitcases around, and you got to drag this big old suitcase that can't hold 8, and it only holds 2, and you're like, why do I have to bring... See, it just makes you unhappy. Like that shopping cart at Walmart with the bad wheel, right? It just makes you unhappy. Atoms are unhappy when it's not full. All right? Now, as you look at the periodic table of our elements, we're going to see the symbol, and here we have the C for carbon. We got the name. We're probably pretty familiar with carbon. It's the basis of all of our organic molecules. Here is our atomic number, and that's the one I want you to pay attention to. Because that atomic number, the number of protons, what did I say the relationship was between protons and electrons? That's the same. So you can home in to that number. Now, I said naturally occurring. There's some instances where you get these radioactive elements and you can offset that balance, but that's not going to be energetically stable, and they're not going to stay that way for very long. For our purposes, that's going to be the same for protons and electrons. Now, the atomic mass that you see, and notice our number for carbon, 12.011. What is that number relative to our atomic number? You got 6 as an atomic number, 12. It's about twice as much, right? Here's another one. Most of our naturally occurring elements, the number of protons is going to equal the number of neutrons. And that's why most of the time that's going to be double. If we have more neutrons than protons, we're something called an isotope, and we're going to talk about that later. And if it gets really unstable, we call it a radioisotope because it becomes radioactive, which most often is not a good day if you're playing with it. Now, here's that big scary chart from middle school and high school, right? You had to memorize some of this stuff, some of the names. Well, we're not going to do that. Because for human biology, there's just a few that are really keenly important to us. Now, the way that this periodic chart was organized, have you ever wondered how it was put together? Lie to me and say, yeah, anyway. You probably never did, right? But the way this chart was put together and why you have some elements on the far left, you have other elements on the far right. This is based on these electron numbers that we have. And these electron numbers are called the valence electrons. It's a big fancy name. Valence electrons simply means how many electrons are in that outermost shell. And do we have a stable situation or do we not have a stable situation? You remember calcium? We just played around with calcium. How many electrons were left in the outermost shell of calcium? 2, because we had 20. Well, there's calcium, and notice it's in the second column from the left. That means there's 2 electrons in that outermost shell. Here's hydrogen. How many electrons are in the outermost shell of hydrogen? That's easy. It's only got 1, so it has to be 1. And so that's why it's in the first column with sodium and potassium. So just the blocks that you see that are coming out at you, and we're going to kind of ignore iron. Iron's present in your red blood cells. It helps carry the oxygen. We're going to focus on these others. Now, here's how I study. And again, like my pyramid with the little 1 letters, I like compressing everything down so I feel like I'm not doing as much as I actually am doing. Because what did I say? Work smarter, not harder, right? So instead of looking at that big chart, I'm just going to look at the boxes. Does that look a little bit better? Now, we need to scooch that over. I don't know why that got off. C is under 4, N and P under 5, O and S under 6, and the CL under 7. And in fact, that still looks too busy, right? Because we got a lot of other numbers and letters in there. Just learn this. You see, that chart was kind of scary, right? Looking at all those. Does that look very scary? You could probably have that memorized before the end of class today, right? 1, Na. Do we know what the symbol Na means? Sodium. H, we already got H, right? Hydrogen. K, that's kind of tricky. Potassium. Oh, wow, y'all are smart. I put it together like that because what town are we in? Knack. See? Knack. N-A-H-K. Knack. 1. Cam. G. You got to kind of throw that glottal. G. Cam. G. Calcium, magnesium. 2. C4, you know why I like putting it that way? C4, blow stuff up. 5, anybody want to be a nurse practitioner? Think about it. Everybody see a nurse practitioner? That's how you can remember 5. 6, so. I got teenagers. I hear that all the time. So, whatever. And then last, 7, chloride. What do the numbers mean again? Valence electrons is the fancy name. What does it mean? How many are in the outermost shell? And if you remember that, okay, I promise there is going to be a question on the test in 3 weeks that's going to ask you how many electrons in the outermost shell of some of those. I'll just straight up tell you that right now. So look, you have already got one of the questions answered on the test. You just have a few more to go, right? But you see how easy that is? Outermost shell of electrons. Now, why am I spending so much time worrying about these electrons in the outermost shell of these molecules that help make up all that we are? Because it's those electrons in the outermost shell that will determine whether an atom can form a chemical bond with a different atom. Now, on that far right-hand side of our chart, in the 8 space, that's where you find elements like neon, helium. These are referred to as the inert gases. What does inert mean? Just give me if somebody says something's inert, it's not going to do anything. It's not going to do anything. It's just sitting there. It's a rock. It's not going to share electrons. If an atom has 8, well, if it has 2, like helium, or 8 electrons in that outermost shell, it's happy, right? It's in its most stable condition. It will not form a bond with other atoms. So that's why we are working with those atoms that we saw that didn't have filled outermost shells. Hydrogen, carbon, nitrogen, oxygen, sulfur and phosphate. These are some others that we're going to see a lot when we look at our organic molecules. So those that have valence electrons, unfilled shells in the outermost shell, they're going to form chemical bonds. And if you're like oxygen and you want to get together with oxygen, then you're going to be a molecule. But if you're different atoms and you form bonds together, the type of molecule you can also be called is called a compound, much like water. And when we think about our proteins and DNA and RNA, those are compounds because there are a lot of different atoms held together by chemical bonds. All because they have valence electrons. All right, again, simple and get more complex, right? Do we all understand valence electrons? Do we all understand that? I am molecule X. I am molecule X. I have an atomic number of 12. Let that sink in. Molecule X. I have an atomic number of 12. How many electrons do I have in the innermost shell? Tried to trick you, didn't I? That's easy. Right, 2. Now, here's the hard one. Molecule X, atomic number of 12. How many electrons in the outermost shell? 2. Anybody have a different answer? How did we arrive at the outermost shell having 2, starting with 12? What do we do with the first 2? That goes in the first one. We start packing the second shell. How many can we pack in that second shell? 8. 2 plus 8 is 10. We started with 12. We have 2 left. See how we did that? Now, as we look at these chemical bonds based on those unfilled outer orbitals, the 3 that we can have are ionic bonds, covalent bonds, and hydrogen bonds. Only 3. We're not getting a big, huge, long list of things. Now, under covalent, we're going to have two sort of flavors, polar and nonpolar, but that's pretty easy. So we're going to start with these 3 bonds, ionic being the first. Because to me, ionic is sort of the easiest for me to understand. Now, an ionic bond means that the atoms that are going to form this relationship together are either going to gain or lose electrons. And when you have an atom that is unbalanced, it has a different number of protons than electrons, we say that is an ion. We can have anions, which are negatively charged, cations, which are positively charged, but notice we still have ion at the end of that name. It's like a battery. Battery, you got an anode and a cathode, right? Positive and negative poles. It's the same thing with our ions. But with our ionic bond, we're going to have atoms that say have 1 electron in that outermost shell. That's not a very stable situation, right? You may have another atom that has 7. That's not stable, right? It's not full. So let's say you're going on a trip and you're taking a friend with you. You've got this big suitcase because you got this one other item that you have to take. So you got to put it in that one suitcase. Your friend has that same big suitcase, but they've got space in that big suitcase for one more thing. What are you going to do? What are you going to ask that friend? Man, can I just put this in your suitcase? I don't have to take my suitcase with me. And your friend's probably, yeah, sure, I got room. Put it in there, right? So your friend carries that extra piece that you had for you, and you can get rid of that suitcase. Now, your outermost shell is full, right? And your friend's outermost shell is what? Full. But now we have an imbalance of electrons and protons. And when we have that imbalance, that's when we're going to get a different charge. And our classic example of ionic bonding is sodium chloride. What is sodium chloride? Salt, table salt. And so what happens with sodium and chloride, sodium's got that 1 electron. It's like, what the heck? Chloride has 7. So sodium says, hey, chloride, can you just carry this electron for me? Chloride says, sure, man, no problem, I got space. When that electron goes to chloride, what is the net charge of chloride going to be? It's got 1 more electron than proton. It's going to be negative. When sodium gives up that electron, now it's got 1 more proton and electron. What is that charge going to be? And what do opposites do? Attract each other until they get married, and then that drives you crazy. Just remember that. Just remember that. I'm kidding. No, I'm not. You understand that? Opposites attracting. When you form ions that are created by the giving away or the accepting of an ion, creating the positive and negative ions, that magnetic charge, if you will, draws them together and you form a chemical bond. Now, this chemical bond is, relative to its strength, it's kind of in the middle of the road. The ionic bond is second of our 3 in strength. It's not the weakest, it's not the strongest. It's just intermediate. But a covalent bond, this is the super glue. When you create a covalent bond, you cannot break it apart. Now, can you break apart an ionic bond? Have you ever done that experiment? You've all done it. If you put salt in water, what happens to the salt? It dissolves. It doesn't just become smaller molecules of sodium and chloride. It actually, the water ionizes the sodium and the chloride, and it breaks that apart. So just placing sodium chloride in water, the energy of water itself, those attractive forces are enough to break an ionic bond. So it's not all that strong. But covalent, yeah, it's the strongest. And the reason it's strong is because the atoms share electrons in a covalent bond. It's not that you give one up or you get one and you have this slight magnetic charge. No, these electrons are spinning around both atomic nuclei at the same time, and it superglues them together. Now, if these two nuclei equally share that electron, then we say that covalent bond is nonpolar. But we have some situations where some nuclei have more protons, and so they keep the electrons around their nucleus a lot more often than atoms they're sharing with that maybe have many fewer protons. And so that unequal sharing is called a polar covalent bond. And we're going to see that in our water molecule. That's going to be our example of polar. So here, for instance, this is nonpolar. Two hydrogen molecules. Is that stable? One electron in your outermost shell, is that stable? No. How many do we want there? We want two. So these hydrogen molecules, they're twins. I have twin boys. I see this all the time. They're like, hey, why don't we share? That way we can have our full shells. And they're like, okay. And so they get together and they share those two electrons equally. So at any period of time, those electrons are equally around one atom and equally around the other. And they're super glued together. But that's not always the situation, is it? Look at water. There are a lot more protons in oxygen than there are in hydrogen. Okay, how many of you have a big brother or a big sister? How many of you are the big brother or the big sister? Okay, so most of us can relate to this, right? Big brother comes to you. Hey, let's share that candy. What is that usually going to mean? Give me your candy, right? Is the big brother or sister really going to equally share? Think about it. Now, all the big brothers and sisters goes, oh yeah, I share. Do they share? No, they don't share. So oxygen is big brother. Hydrogen is two little brothers. Oxygen says, hey, you know what? You got one electron out there. I'll tell you what, if you share yours with me, I'll share some with you. That way you can have two. Says that to both of them. Now, look at oxygen. How many electrons has it got out here? 2, 4, 6, 8. Oxygen's happy. Oxygen's like, oh, yeah. And because of all those protons, look at these, just these couple of electrons. See where they're staying more around the oxygen? And every now and then one slips out here to that hydrogen. When you unequally share the electrons, it creates a slight negative charge around the oxygen atom because the electrons stay there more often. And since the hydrogens, they get electrons way fewer times, way fewer orbits, there's going to be a slight positive charge. Do you see how that's different than ionic? Ionic, you're giving or accepting electrons. Here, you're unequally sharing. Both are creating situations where you have charge differences. Ionic, remember, intermediate strength bond. Covalent is the strongest because they're sharing. But we're still going to talk about water. Because water can be an example of our polar covalent bond, but water can also be an example of our third one, the hydrogen bonds. The weakest of our bonds. Because when we look at water molecules, because there is a polar situation with how they share electrons, that negative side of the water molecule is going to attract other positive molecules, including other positive sides of water molecules. Have you ever been waxing your car and you see that drop of water run down the hood of your car and it gets close to that other drop and then all of a sudden it's like they get sucked together? It's like magnets. That's hydrogen bonding in action. It's the hydrogen bond that holds our water molecules together. So in this illustration here we have 3 water molecules, well actually 4 water molecules. Remember the oxygen side is negative, the red circle. The blue hydrogens, those are positive. And those little dotted lines, those are simply the attractive forces of the slight positives and slight negatives holding those water molecules together. Now, I asked you earlier, have you ever broken ionic bonds? Remember, that was putting salt into water. Well, remember, salt is comprised of ions, right? Positive and negative ions. Do you see why the salt falls apart in water? Because water has a slight negative and a slight positive. There's so many more water molecules when you put some salt in that water. It ionizes the sodium and chloride and creates a bubble of water molecules around each ion so that they can't get together. It's like a competitive thing. Now, have you ever broken hydrogen bonds? Have you ever done the experiment where you break hydrogen bonds? Everybody? If you haven't, you need to get in the kitchen because clearly somebody's not teaching you right. How many of you have ever boiled water? Let's try that one. Have you boiled water? Boiling an egg, right? When water converts into steam, the water molecules are moving so fast, steam is much less dense than water, right? Why? Because you're breaking hydrogen bonds. Have you ever slowed down hydrogen bonds? You put water in the freezer, make ice. You're making those hydrogen bonds even tighter. So you see, a lot of this chemistry stuff that you're scared of, we use all the time. We just don't realize we do. But those are the three bonds that are responsible for forming our biologically important molecules. Ionic, intermediate strength, covalent, superglue, and hydrogen, the weakest of our three bonds. All right? Make sure you know those bonds, how to define those bonds, and what their strength is. You'll see it on the test. Now, this is another sort of biology example of why it's important to understand the chemistry. Who can tell me what that molecule is? That's DNA. You see that model in the back of Sheldon's living room, right, on the Big Bang Theory. DNA is a double helix. Have you ever heard that before? One of these strands of DNA is going to have one code on it. The other strand is basically the backup code. And whenever you are going to produce an offspring, one of those strands is going to be used to go into one egg or one sperm. The other strand is going to be going into the other egg or the other sperm. When your cells have to replicate for new skin or new cells that line your stomach, the cells that line your stomach, they're exposed to hydrochloric acid. Did you know your body makes hydrochloric acid? That's kind of freaky. I think of that alien monster, you know. But your body makes hydrochloric acid, and those cells that are exposed to it, they die every 5 to 7 days, so you have to make new cells. And the way you make new cells is you take an existing cell and an existing molecule of DNA, you split it apart, and make two brand new strands so that one can go to one daughter cell and the other can go to the next daughter cell. That, you would say that's an important process, right? Wound healing and normal growth. Well, if these two strands of DNA were held together with covalent bonds, would you ever get them apart? No, you wouldn't. So, what bonds our two strands of DNA together are hydrogen bonds because they have to be broken and they have to be able to be reformed fairly easily. So that's another important reason why we understand the bonding energy of our atoms. All right. So let's look a little bit more closely at some of our molecules. We're getting more complex now. See, we're adding more C's and more H's and more O's. I told you we'd start simple, and we did, right? Hydrogen. As complicated as we got so far, it's sodium chloride with 2, water with 3 atoms. All right, we're adding a little bit more. So we talked about our polar covalent bonds. How do you share electrons in a polar covalent bond? Equal or unequal? Unequal. If it's polarized, meaning you got a positive and negative, it has to be unequal. If it's non-polarized and both sides have the equal charge, then it has to be equally shared. Here is such a case. We've got the same number of hydrogens bonded to these carbons, and so here we have a non-polar molecule. And there are a lot of names that we can describe and ascribe to that kind of molecule. One of those big names is called hydrophobic. Now let's break that word down. Phobic, phobia, what does that mean? Fear, you're afraid of something. Hydro, water. So in this case, a non-polar molecule, primarily composed of carbons and hydrogens. We also call these hydrocarbon molecules. These are said to be hydrophobic. They don't necessarily fear water, but they don't mix well with water. You cannot dissolve a hydrophobic molecule in water. Where else have you heard about something not mixing with water? Oil. So, what category of molecule would you consider oil? Oil is hydrophobic. Oil is also a hydrocarbon molecule. Gasoline, diesel, these molecules are hydrophobic, and so they don't mix well with water. Now, molecules that do mix well with water, such as polar molecules and ions, they are said to be hydrophilic. Philic comes from, I think, the Greek philios. What does philios mean? Have you ever heard that word? Love. Hydrophilic, water-loving. So polar molecules love water. They'll bind and interact with water all day long. You can dissolve them in water. Hydrophobic, not going to happen. But as we build up, bless you, our biological molecules, we have these other molecules that can kind of do both. Do we have an animal in the animal kingdom that lives in two different places? Sometimes on water, sometimes on land? Huh? Amphibians. You ever heard that word before? I'm a big war movie fan. If it's got John Wayne in it and he's wearing green in World War II, I'm going to watch it. And a lot of those movies where they're coming in at Normandy and stuff, they're coming in on these landing craft because they're partly boats and then partly they can drive on water. What kind of vehicle is that? An amphibious landing craft. So here we have a molecule that part of it, the head of this molecule that we see here, is polar. But then we have these chains coming off of it that are non-polar. See, it's a much more complex molecule. But since we have part that's polar and part that's non-polar, we say it is not amphibious. But you see how we get kind of the same thing? Those kind of molecules are said to be amphi for both, pathic. And as we begin to build up all these molecules so that we can produce our organelles, remember that's about our next level as we go, and then our cells, we're going to be using polar, non-polar, and amphipathic molecules to do that and to put them all together. Now, before we get into our organelles, water. Got to talk about water. Why in a human biology class would you think it would be important to talk about this boring compound called water? That's what we're mostly made of, right? I like the old Star Trek TV series. And there was one episode way back, way before you were born. But there were these rock creatures. And when they finally were able to communicate with the humans, they called them ugly bags of mostly water. I mean, I don't think we're ugly, but we are. Bags of mostly water. Now, we've already seen how we're polar, right? The covalent charge, the unequal sharing, makes us polar. What bonds cause water to be cohesive? Which of our three chemical bonds cause water molecules to be cohesive? stick together? Hydrogen bonds, right. So covalent creates this situation, hydrogen creates this situation. Now, it's largely because of this polar situation that water is referred to as a universal solvent. About the only thing that water cannot dissolve are going to be those hydrophobic molecules. But the other thing that's great about water, well, depending on the time of year. In the springtime, when it's starting to get warmer outside and the sun's out a lot, and you're ready to go swimming, what is it you realize about water? It doesn't heat up that fast, right? Our boiling experiment. What is the old saying? A watch pot never what? A watch pot never boils, because it seems like it takes so long. But likewise, if you want to cool off, and the rec pool over here, especially that shallow part, man, in the hot part of summer, it's like bath water. Even when you go at night after a sunny day, it's not very cool. Because water has a tremendous ability to stabilize temperature, to stabilize energy within it, because of this cohesive nature of these molecules. So water's not going to heat up real fast, and it's not going to cool down real fast. Which is great if we're mostly water, because do we want our temperature to go way up and way down all the time? No. Worst thing in the world about having the flu is when you're running that temp of 102, 103. That's for ladies. Guys, we have 99 and we're in the emergency room. It's the man flu. It's scientific. Look it up. I'm serious, really. A paper came out. Did you guys all see that? You need to have that reference in your back pocket. There is a physiological paper that says males respond to illnesses differently than females. We're not wimps. We're not. I'm trying, right? No, I'm serious. There is a paper. All right, we've already talked about our hydrogen bonds again, holding our water molecules together. Boiling point. When does water boil? 100 degrees centigrade. 100 degrees centigrade. Fahrenheit, it's what? And how they came up with this number? 100's a lot easier for me to remember. Fahrenheit, it's 212. 212. It's weird, when I'm here and I'm in my nerd scientist hat, I can only use centigrade. When I go home, I can't use centigrade. I like to cook sometimes in the measurements instead of milliliters and stuff. I got to do cups and teaspoons. I can't go back and forth. It's crazy. Surface tension. Do we understand surface tension? Have you ever seen those insects that can walk on the surface of the water? I think they're called water striders. Their legs don't push down through the surface of the water. They just kind of make a little indentation, but they don't actually go through. That's because the weight of that insect and these tiny, tiny hairs on its legs exerts an equal amount of force over a greater area, such that its weight can't break the hydrogen bonds. So the strength of the bond between the molecules is stronger than the weight of the insect pushing down, and so it just scoots along the surface of the water. You may be thinking, okay, this is human biology, it's not entomology and about bugs. Well, this surface tension, the strength between those bonds holding water molecules together, are critical to you being able to breathe when you are first born. How many of you have ever had family members with premature babies? One of the biggest dangers for preemies is the ability for them to breathe. Because there's a substance that the cells inside the lungs make. It is a hydrocarbon. It is hydrophobic. But it also has a polar head, which means it's got both polar and hydrophobic. And what was that big fancy name? Not amphibious, what was it? Amphipathic. It's able to disrupt the water molecules and break up that surface tension. Because the surface tension of the water molecules inside these little spaces in the lungs for these preemies is strong enough to close up the lungs. And so the air can't get in. The oxygen will never get to the lungs. People that have acute respiratory distress, sometimes that can happen to them. So you see, surface tension, it's not just about insects, but it's about the human body at different times of our development. All right, so water is a solvent. We've already talked about this. I'm going to give you a chance to look at this slide. We're not going to belabor this too much, but water is a universal solvent. If you remember that statement, I almost promise you're going to use that at some other point in your life, and you're going to go, wow, there was this crazy biology professor taught me way back when. He said that. Well, at least he was right about that. Water is the universal solvent because it's a polar molecule. That's its biggest benefit. So here's our sodium and chloride, right? We talked about. You drop sodium and chloride in. You see how these water molecules have surrounded them? These ions, they can't get back together. And so some call that hydration shells. I've heard it called sphere of hydration. It's just a big ball of water that surrounds all those ions. Here's our oil and water doesn't mix. Have you ever done that and put oil and water in a jar and then shake it up and it looks like it's kind of together? But if you let it sit, it layers out and the oil rises to the top. Because at the top, these molecules are hydrocarbons, which are nonpolar, and they're what? Phobic. Whereas water molecules, I guess water molecules are hydrophilic because they love water and they are water. Okay. But as we begin in especially the next chapter, when we talk about cells and membranes, and a little bit when we talk about organelles here, we're going to see that we have molecules that are put together in our membranes. And these molecules that form the membrane of our organelles and the membrane of the cell itself, these are going to be amphipathic in nature. They'll have a charged portion, these little round spheres, and then these chains coming down, those are going to be our hydrophobic, non-polar hydrocarbon chains. And we'll get to those in a bit. All right, last little thing about chemistry before we get to our organelles is acids and bases. Now again, in chemistry, this is one of those things that, I had the hardest time really understanding because of the technical nature of acids and bases. If we've got hydrochloric acid in our stomach, we kind of need to understand acids. And we also have cells in our body that produce sodium bicarbonate, which is in fact a base. Because again, we're trying to reach this balance within our body. So, acid. Here is the really technical definition of what an acid is. Are you ready? An acid gives off a hydrogen. That's it. Gives off a hydrogen. If you put something in water, and from that something you get hydrogen ions, that something you put in the water is acid. The stronger the acid, the more hydrogens are going to be freed up by that substance. So strong acid, hydrochloric acid, that's pretty strong. Wouldn't you say hydrochloric acid is pretty tough? So it's going to give up a lot of hydrogens. But we also have acids in our body. Carbonic acid, it doesn't produce as many hydrogens, and that hydrogen doesn't dissociate nearly as quickly. And so it's a weaker acid. Now here's a little preview. When you transport oxygen and carbon dioxide in your blood, you probably already have a pretty good guess that your red blood cells transport the oxygen, right? Most people probably get that part. And if you're anemic, if you don't have enough red blood cells, you're going to get weak, you're going to feel run down. Here's a trick question. Do your red blood cells also transport carbon dioxide from your tissues back to the lungs? Everybody shake your head no. They don't. Red blood cells take the carbon dioxide, and because of enzymes, they convert the carbon dioxide first into, guess what? Carbonic acid. That carbonic acid then is released into the plasma, the liquid part of your blood, as a bicarbonate ion. And that's what flows back to the lungs. That conversion process is reversed. You produce carbon dioxide again. That moves into your lungs and you exhale. So if you didn't make carbonic acid, you wouldn't be here. You wouldn't be here. You have to have hydrochloric and you have to have carbonic for you to exist. Now, a lot of times in science, you are going to have things that are opposite. And I love when you get to situations where things are opposite. You know why? Because you only have to learn one thing. Because an acid, what did we say our definition of an acid was? Gives off hydrogen. If I tell you a base is opposite, what does that mean? It's going to accept it. So do you have to remember that a base accepts hydrogen? No. Just remember acids give off and bases are opposite. You know twice as much, but you're only memorizing half. Smarter, not harder, right? But that's a base. It's something that picks up hydrogens. Again, that bicarbonate that we were just talking about in your blood. Yeah, it's going to pick up some of those extra hydrogens that are around because the carbonic acid, some of this in your digestive tract, that's going to pick it up from the hydrochloric acid in your stomach so that it doesn't do damage to your intestinal tract. Now, we've got some really strong bases, ammonia, bleach. We don't make those in our body, okay? Yeah, our body doesn't make that kind of stuff. But that's a proton acceptor. Bicarbonate's the one that we're going to play with later in the semester, especially when we get to circulatory system or digestive system. But it is in fact a base because it accepts a hydrogen ion. And anytime you see that little plus or negative, that means that's an ion. Okay, I haven't explained that to you before, but that's why I keep calling that a hydrogen ion. You know what some people also call a hydrogen ion? A proton. Because what is it? It's a hydrogen that's given up its electron, so what's all that's left? A proton. That's all it is. Just a little proton all by itself. All right, so we have been talking about chemistry. Now when we stick this bio in front of it, do you remember what we said bio and biology meant last week? Bio is life. So here we're talking about the chemistry that really involves the substances and compounds that are critical for life. And basically we got two choices here. We got organic or inorganic molecules. Organic has what? Carbon. Guess what? Inorganic's the opposite. So an inorganic molecule doesn't have what? Carbon. Yeah. See how easy? Opposites. I love opposites. So we're going to focus mostly with our organic molecules and look at how these different categories of these organic molecules are critical to us being here, us being alive, growth, development, wound healing, all of the above. So as we look at these organic molecules, in almost every instance, we're going to have four big categories of these molecules. Carbohydrates, proteins, nucleic acids, and lipids. In almost every one of those categories, we are going to easily see that they are put together as building blocks called monomers. It's almost like, I've got two granddaughters, and when they were little, they played with those plastic sort of beads, you know, that's got the little pointy thing on one end and the hole on the other, and you can put them together and make a necklace and a did y'all remember playing with those things? Oh, y'all play with iPhones when you were kids. That's all we had when I was a kid. But these things that you can link together, well, that's what we're doing here. These individual building blocks are called monomers, mono meaning one. And you can link them together in these long chain of molecules that we refer to as polymer. Poly means many. And once again, whether we're talking about sugars, carbohydrates, or proteins, or even nucleic acids, you've got these building blocks, these individual units that you begin to assemble together, and you can form critical molecules like DNA or glucose, or for that matter, hemoglobin, which is the molecule inside red blood cells to transport oxygen. Now, the way your body works, again, opposites. So the way your body takes these monomers, let's say this is a simple sugar, and we're going to see this as we go through. You use enzymes that can take these two individual units and link them together. And in this case, we've taken two individual units and put them together into a dimer, meaning a molecule composed of two units. But what is produced in the process? A molecule of water is liberated. You take a hydrogen from one and you take a hydroxyl, an OH group from the other. You release a molecule of water and you join them together. This is referred to as a dehydration reaction, or you can also call this a condensation reaction. Because when you get condensation on the mirror of your bathroom after a hot shower, what are those drops made of? Water. When you dehydrate, what is your body losing? Water. When you put these together, what are you losing? Water. Now, there are going to be instances where your body wants to take these individual units and link them together. A great example is going to be carbohydrates. Your body stores sugars in long chains. But just like it can store sugars that way, your body's going to need to use it at some point. So your body's going to want to go break off a piece and use it for fuel. Kind of like a Hershey candy bar, right? It's got those little bricks. You go, does anybody break off one of those at a time? I can't. I peel that sucker. I look at them. I think about breaking it off, but I'm just like, I'm a chocoholic. I love my chocolate. But basically, the breaking off the individual units from chains is the opposite of what we see here. If we took this picture for dehydration synthesis and did nothing but change the direction of those two arrowheads to make this line go up and make this water come in, that then is the illustration for what we refer to as a hydrolysis reaction. And you can basically see it here. We take our dimer, we add water using enzymes, break them apart. Hydro, water. Have you ever heard this word lysis or lyse? What does that mean? To cut or to break. So here hydrolysis is using water to break the dimer into two monomers. But again, if you remember dehydration, you just remember hydrolysis, the opposite. Dehydration, building up. Hydrolysis, because you got that lysis in there, breaking down. And it's all referring to monomers versus polymers. Does everyone understand that? Again, I've been saying carbohydrates, but this is still a general concept that we can apply to several of our lists of biological molecules. Carbohydrates is just one of the most obvious. So here's an example of some of these molecules and how they're organized. But when we talk about organic molecules, what is the key player in that? Carbon. And the reason carbon is so important in organic molecules, carbon has a valence of how many? Remember C4, explosive? That means carbon can form bonds with 4 other molecules. Now, there are times that carbon can form double bonds. There are times that carbon can form even triple bonds. But carbon is a great link to put molecules together into either rings like we see with some sugars, chains, branch chains that we'll see, very, very complex molecules. But carbon seems to be right at the center of most of these biologically important molecules. And so right now, life on Earth is carbon-based. That's our understanding. And it's interesting when we go to Mars and we're looking out into space at some of these Earth-like planets. We're going and investigating all these things, looking for carbon-based life forms, but we may find something completely different. But we have to start somewhere, start simple, start with what we know, and build from there. All right, so now let's get into the meat of some of our macromolecules, our biologically distinct groups. And here are the 4. Again, simple, right? We had 3 bonds. Notice we had 4. Okay, we're building up as we go. So our 4 groups of biologically important molecules: proteins, nucleic acids, carbohydrates, and lipids. We're going to take each one of these and expand on them. But particularly, I want you to pay attention to what are the monomers for each one of these versus what are the polymers. Lipids are the group that doesn't work so well for them. That's why I put them last. But certainly for proteins, nucleic acids, and carbs, monomer, polymer is what I want you to pay attention to. So proteins, let's go there first. What are some of the functions of proteins? That's a bunch. And you know what? That's not even an all-inclusive list of what proteins can do. We have enzymes that facilitate chemical reactions. We have proteins that help maintain the shape of certain cells. If it wasn't for proteins, red blood cells wouldn't have that. Scientifically, it's said a biconcave shape. You know what I'm talking about? The red blood cell? Where it's got the indentation on both sides? That's a biconcave shape. For me, I say it's a squished jelly donut. That's how you eat jelly donuts. You know that, right? You got to squish all the good stuff out first, then you eat the donut. That's not how you eat a jelly donut. How are you supposed to eat a jelly donut? Just a bite of it. You just bite into it? You squish the stuff out, right? What? You don't? You do know they have chocolate-filled donuts now. That's the bomb. That's the bomb diggity right there. But if not for proteins, red blood cells wouldn't have that shape. Cells wouldn't be able to move. Transport. This is so critical for everything. Without transport, all that you ate, all that good nutrient wouldn't be able to make it into your bloodstream. Right now, we are so glad we have proteins that are available for defense of our immune system, right? Who has had the flu this year? Not right now, I hope, right? Okay. How long ago? See y'all later. Man, the flu is bad this year. Bad. And many of you probably were exposed to the flu virus, especially if you're sitting right there. But your immune system and the proteins that detect those viruses and activate your immune system kept you from getting sick. So proteins, extremely, extremely important. Now, based on what we talked about with our biological molecules, could somebody shut that door, please? Could you just pull that too? What in the world's going on out there? How big was that class? Our monomers versus polymers. Proteins are the polymers. And again, proteins in many ways can look like a pearl necklace. And so as the whole necklace, could you get that? Are the proteins, each bead, each monomer of our proteins are amino acids. again, on the test, can almost promise you you're going to have a question about what are the monomers of such and such and so and so. Almost promise you. And for our proteins, as we take these amino acids and we line them up and we assemble them, we're going to form a bond between these two amino acids that's going to result in the liberation of a molecule of water, that dehydration reaction. But in this case, we call it a different bond. This is, in fact, a covalent bond, which is the strongest, right? Because we want our proteins stuck together. But the type of bond that we have between the amine group of one amino acid and the carboxyl group of a second is referred to as a peptide bond. That only really exists, and you'll only hear that term in reference to proteins. And that's why sometimes proteins are also called polypeptides. Right? Because of that peptide bond. You want me to tell you how important proteins are? If you had to think of a molecule in all of your cells that was the most important molecule, it defined everything that you did. It had the code for how you look, how you act. What would you say that molecule is? You're not going to have babies without this molecule. DNA, right? The genetic code. What does that genetic code actually do? That code is used to build proteins. That's all the code does, is build proteins. Proteins are, in fact, the workers. The DNA is just the code for how to make proteins. That tells you how important proteins are in their assembly. Now, an amino acid is a basic unit that you'll see here. But amino acids, and we're going to have 20 different types of amino acids. Don't worry, you don't have to know them all. But they're going to have these groups where you have this letter R. That R group means this is the variable portion. Why they didn't make it the V group, I don't know. But you got the amine group, you got the carboxyl group, and you got a little hydrogen sitting up here. This is the group that is going to define the characteristic of that particular amino acid. Whoops. So you see how some have these kind of big rings. Here's the simplest. That's just a methyl group. That's going to be the amino acid glycine. Here we have a fairly long chain. And we've got a little sulfur kind of stuck in there. That's the amino acid cysteine. But each one of these is going to have different properties. This amino acid is going to be great in places of proteins where you got to make a tight twist or a tight turn, because there's not much there to get in the way. You're not going to put that in a turn or a bend. It's too big. So first, amino acids, the monomers of proteins. That sequence of amino acids is referred to as the primary sequence of a protein. You know, we talk about DNA, and we'll get to that probably on Thursday. You know, A, T, C, G, you see those four letters put together, that's your genetic code. Well, with amino acids, you can sort of do the same thing. These single letter abbreviations for amino acids, a primary sequence might be something like M, A, K, L, Y, R, D, G. And that sequence of how they're put together and the order that they are assembled is called the primary sequence of your protein. Now, because our amino acids also have the capacity, many of our amino acids have the capacity to form hydrogen bonds. When they form hydrogen bonds, either in a spiral arrangement, much like you might see with DNA, or sometimes it goes back and forth across itself, making a sheet, that is referred to as the secondary structure, or the initial folding up of our protein, because our protein is going to fold itself into a three-dimensional shape. Well, that final three-dimensional shape that we see in this particular case, that is called the tertiary structure. There are other amino acids and other atoms that are going to help form bridges across parts of this primary sequence that causes it to take on this final three-dimensional globular shape. There you can see one of our spiral helices. We might have a beta sheet more in the middle in this location, but that's the tertiary structure. Now, the last level of organization of proteins, if we take a couple of different protein chains and we link them together into a much larger molecule that we see here. See, there is our protein chain, that's our tertiary structure. But we take 4 of those guys and we put them in this. See, 1, 2, 3, 4. That molecule now has a quaternary, 4th level structure. That's the pinnacle, that's the top. We're not going to have 5. The 4th level is the top. And so in this case, we have a molecule that is basically built of 4 interconnected protein chains into its final fully functional state. And in fact, that molecule that you're looking at right there with that quaternary structure, that is hemoglobin. And hemoglobin is going to have the capacity to bind 1, 2, 3, 4 molecules of oxygen as this transports oxygen around in your bloodstream.